Now, the next topic is equivalence classes. We define equivalence classes in this way. Let R be an equivalence relation in a set A and element A belongs to set A. Then the set of all those elements of A which are related to A is called the equivalence class determined by A. The set of all those elements of A which are related to A is called the equivalence class determined by A, and it is denoted as box A. This is how we are going to represent box A. So, an equivalence class of A is set B, which is in A, such that AB belongs to R. So B is the element which is related to element A. Then set of all those elements which are related to A will form an equivalence class for this element A, and it is denoted as box of A. We'll take one example to explain more clearly what is an equivalence class. Just remember these two important results. Two equivalence classes are either disjoint or identical, and an equivalence class or equivalence relation R on a set A partitions the set into mutually disjoint equivalence classes. An equivalence relation R on a set A partitions the set. It will make partitions of the given set on which your relation is defined into mutually disjoint equivalence classes. Now in one next example, I'll show these two results. What is an equivalence class and how this result can be verified that equivalence relation R is partitioning the set into mutually disjoint equivalence classes. One example, on the set Z of all integers, consider the relation R is equals to AB such that A minus B is divisible by 3. Show that R is an equivalence relation on Z. Also find the partitioning of Z into mutually disjoint equivalence classes. So first we will show that this R is an equivalence relation. So first step is to show that it is reflexive. Let A belongs to Z such that, now A is an integer, so we'll go through the definition that A minus B is divisible by 3. So if it is a reflexive relation, then it means A minus A, which is 0, and 0 is divisible by 3. So A minus A is verifying this definition. So it means we can say that AA belongs to R, or A is related to A. This means R is reflexive. Now we'll show that it is symmetric as well. For that, let A and B are in Z such that AB belongs to R. If AB is in R, it means A minus B is divisible by 3. Now, if A minus B is divisible by 3, we can say that minus of A minus B is also divisible by 3. Now if you open the bracket, it will become B minus A is divisible by 3. If B minus A is divisible by 3, it means BA belongs to R. Now AB was in R and we found that BA is also in R. It means R is symmetric. Let A, B and C are in Z such that AB belongs to R. It means A minus B is divisible by 3 and BC belongs to R means B minus C is divisible by 3. Now A minus B is divisible by 3. It means A minus B is a multiple of 3 and then B minus C is also divisible by 3. So if we add these two numbers A minus B and B minus C, so their sum is also divisible by 3. This means A minus B plus B minus C is divisible by 3. Right? So when we open the brackets, this B and B will be cancelled out and we'll get that A minus C is divisible by 3. Or we can say that AC belongs to R. So AB was in R, BC was in R and we found that AC is also in R. It means R is transitive. So as R is reflexive, symmetric and transitive, we can say that hence R is an equivalence relation. So this first part is proved. Now we'll show that the partitioning of Z into mutually disjoint equivalence classes. For the second part, that is the partitioning of Z, we need to define equivalence classes. Now, how to define equivalence classes? For that, you need to consider or you need to just look at the case. It is A minus B is divisible by 3. If you look into the set of integers and if you divide a number by 3, so there may be 3 cases. Either it will be divisible by 3 or it will give you a remainder 1 or remainder 2. Right? So just 3 cases will be there. So it means we can divide whole set of integers into 3 partitions. One which are divisible by 3, the other one which will give you a remainder as 1 and the third one which will give you a remainder of 2. So I am considering 3 cases, 0, 1 and 2. So now, what does this equivalence class box 0 means? It means that set of all those elements which are related to 0. It means X belongs to Z such that X minus 0 is divisible by 3. So now we need to list all those elements which will verify this property, that is X minus 0 is divisible by 3. So it will consider or it will contain all the elements which are multiple of 3. So we'll list out all the integers which are multiple of 3. So equivalence class for 0 will be this set. All these elements are related with 0. Now the second will be 1. It will be a set of all those elements which are related to 1. Or we can say such that x minus 1 is divisible by 3. So now you need to list out all the elements which will verify this property. So we can list out 4 minus 1, right? Minus 5 minus 1, then minus 2 minus 1, 1 minus 1, 4 minus 1, 7 minus 1, and so on. So this is the equivalence class for 1, and these are the elements which are related to 1. You can check that 4 minus 1 is divisible by 3, 7 minus 1 is divisible by 3, and the next number will be 10. 10 minus 1 is divisible by 3. 1 minus 1, that is 0, is divisible by 3, and so on. You can check. So this is the equivalence class for 1. Now the third one is equivalence class for 2. It means x belongs to z such that x is related to 2. So it means it will contain all the elements from z which are related to 2. Or we can write it as that x minus 2 is divisible by 3. So now we'll list out all the elements which are related to this condition. So it will be, so we can start with first 2, because 2 minus 2 will give you 0, and 0 is divisible by 3. Now keep on adding 3 to this side, so it will be 5, then 8, and so on. And on this side, start subtracting 3, so it will give you minus 1, then minus 4, and so on. So these are the elements which are related to 2. You can check minus 4 minus 2, that is minus 6, divisible by 3. Minus 1 minus 2, that is minus 3, divisible by 3. 2 minus 2, that is 0, divisible by 3. 5 minus 2, that is 3, divisible by 3. 8 minus 2, that is 6, divisible by 3. So now we have all three equivalence classes. What is asked? Find the partitioning of Z into mutually disjoint equivalence classes. Now I am writing all three together. What was 0? It was minus 6, minus 3, then 0, and 3, 6, 9. This is the first partition of Z. Second is 1. What was that? Minus 5, then minus 2, 1, 4, 7, 10, and so on. And the last one is 2. It is minus 4, minus 1, 2, 5, 8, and so on. If you look at it carefully, there is nothing common in all these three classes. So it means they are mutually disjoint. And we can write our Z as this union equivalence class of 1, union equivalence class of 2. So these are the three partitions of the given set Z. I hope it will give you some clarity about equivalence classes, equivalence relation. So this is all about the syllabus of grade 12 for relations. Keep watching M for Mathematics, and now in the next video we'll start with the topic functions, which is again a very important topic from the point of view of competitions and your board examinations as well. Thank you for watching.